Hey guys, welcome back to another video. In this video, we're going to talk about gravitational field strength. Up till now, we learned about how to find the orbital velocity, how to find the force between two-point mass, and what different types of orbits are, polar orbits, geostationary orbits, and how to achieve those orbits. We also learned about Kepler's law, how radius and time period varies, and in case of orbits, we learned how circular motion is related to gravitational force. Now, in this case, in this video, we're going to learn about gravitational field strength. That is, for a specific point mass, let's say this mass, this planet, what is its gravity or gravitational field strength going to be? Now, near the surface, it is going to have a specific gravitational field strength, that is a set amount of force per unit mass, and at a different distance, I'll mark it with orange, at a different distance away from the point mass, it's going to have a different force per unit mass. That means different gravitational field strength, a different gravity. Now, in our case, we have always heard that gravity is set to be 9.81 in case of Earth. But it turns out to be that as you move away from a point mass, in our case, considering the planet Earth, as you move away from it, that is, as the separation increases, the gravity turns out to decrease, which means with varying distance, with varying separation away from the point mass, your gravity or gravitational field strength will decrease. Now, to understand that better, let's define what gravitational field strength is, right? So, gravitational field strength at any point is defined by the force per unit mass. Therefore, if this is your point mass, at any given distance, what is the force per unit mass exerted? Therefore, if I have 1 kg object over here, that is 1 meter away from the point mass, what is the force going to be exerted? And at this distance, 2 meters away, what is the force going to be exerted? And at 3 meters away, what is the force going to be exerted? On, mind you, 1 kg of mass. Because it's talking about gravitational field strength per unit mass. So we're going to think of this in terms of what force is exerted on 1 kg of an object due to any isolated mass. In our case, let's talk about planet Earth, right? So what is the force per unit mass at any given distance? That is what gravitational field strength is. Now, how can we derive gravitational field strength? So in this part, we'll talk about deriving the formula of gravitational field strength. Now, let's take two masses. One is M1, consider it Earth. The other is M2, consider it anything, any rock or let's say moon. So these two masses are affected by each other's gravitational field. That is, we will have a gravitational field that is inwards for M1. You have another gravitational field that is inwards for M2. Now what happens is both of these gravitational fields interact and both of these pull the other mass towards its center. So M1 is going to pull M2 towards its center and M2 is going to pull M1 towards its center, right? Now, what that at the end of the day results in is a net force, a net gravitational force, Fg. This Fg turns out to be the same for both masses due to Newton's pair of force. Action force is equals to repulsion force. So that is Newton's third law, right? So that is a weight over here since Fg on M1 is the same as Fg on M2. Now, taking that into consideration, let's derive our gravitational field strength. Now, you know two formulas. That is, one is of Fg In the first video, we talked about how Fg equates to Gmm by r squared. So gravitational force is given by this formula. You also know another formula, which is F is equals to mg. This is something that we have learned from a very young age. The net force on any object, be it this pen, be it the mouse, be it anything, is going to be mass times the gravity or the gravitational field strength. This G denotes gravitational field strength. Therefore, at the surface of Earth, we all watching this video are at the surface of Earth. And at the surface of Earth, there is a specific gravitational field strength near the surface, that is. So this G denotes that gravitational field strength. So mass times gravitational field strength, in our case near the surface, is 9.81, gives you the force, the net force. So if we make the gravitational field strength the known formula, the subject, right, we're going to get F by m, right? This is one of our formula. So let's take this into account. And the other formula, as mentioned, of Fg, let's take this into account, right? So both of these formulas, you know, and what I'm going to do next is I'm going to equate this formula and this formula. F is equals to mg. This is the mass m2, let's say the moon, times gravitational field strength of the mass of Earth, that is the field strength due to the mass of Earth. So at this given distance, what is the gravitational field strength of Earth? That is denoted by G. So G times m2, the mass of moon, is going to give you the gravitational force. Great. So now you'll equate equation 2 in this part. Now what you're going to get is Gm is equal to Fg Gmm by r square. So you have equated the two force formulas known to you, and what you get at the end of the day is the formula for gravitational field strength, Gm by r square. That is the mass of Earth, whose gravitational field strength you're measuring, divided by the separation at which the object is, the m2 mass is. Therefore, gravitational field strength is given by the gravitational constant times the mass of itself divided by the separation squared. Now, there was a simple way to do this. That is, if you had taken the net force, that is Gmm by r square, and just plugged in the value m is equals to 1 kg, you would have gotten the GFS formula, Gm by r square. Because remember, what the formula tells you is gravitational field strength is the force per unit mass. It is still the force, but with respect to 1 kg of mass, right? So, due to the gravitational field of Earth, what is the force going to be exerted on 1 kg of mass? It is going to be given by this formula, Gm by r square. So let's say you're 2 meters away from Earth. What is the gravitational field strength at that point? It is going to be Gm by 2 square. And if you know the gravitational field strength, and if you know the gravitational constant, and if you know the mass of Earth, you can find out the gravitational field strength due to the Earth's mass, right? So this is how you can figure out the gravitational field strength at any given position. Notice the separation, the radius away from the center of Earth is going to affect your gravitational field strength. And we are going to see how the effect varies with different separation. Great. So we understood the formula of Gm by r square. The same could be done with the mass of moon. So using the mass of moon, you could find its gravitational field strength. So you would have plugged in for the gravitational field strength of moon. What you would do is the gravitational constant, mass of moon, that is m2, divided by the separation at which the Earth is. Now mind you, this would actually give you a lower value compared to the gravitational field strength of Earth. Now you may be confused that isn't the force Fg supposed to be the same in both cases? Yes, it is supposed to be. Because in our case, what you have found out using the formula is the field strength, not the net force. So the moment you multiply this gravitational field strength with the mass of, let's say, Earth, m1, you will get the net force. Similarly, in this case, the moment you multiply this g with the mass of moon, you will get the same Fg. So therefore, Newton's law of gravitation does not get disobeyed, right? So next up, we're going to learn about the gravitational field strength at the planet's surface, in our case, Earth. So we're going to see what the gravitational field strength is near the surface of Earth, right? Now, we already know the value G is equals to 9.81. Let's see if we do get this value, right? So now we know the formula of gravitational field strength, which is G times mass of Earth, the field strength of which we want to find out, and the separation. Now, in case of the separation, remember, we measure from the center of Earth, or the center of the mass. Now, the center of mass turns out to be over here, and this value is going to be the radius. And let's say you want to find out the gravitational field strength at a small distance above Earth. Let's say 2 meters above the surface, right? So what you're going to do is gravitational constant times the mass of Earth divided by r, the radius of Earth, plus the altitude at which you're measuring the field strength to the power of 2, right? So now, after you plug in all the values, what you're going to see is, since the h, the altitude that you're taking, let's say 2 meters above the Earth's surface, is very small compared to the radius of Earth, which is actually really big. Now, compared to that, since it is so small, we are going to say r plus h is approximately the same as only r, since the h is not going to vary the amount, right? So in that case, we can write gm by r squared, in which case the answer turns out to be 9.81 newtons per kg. If you want to find it out yourself, you can plug the values of gravitational constant, you can search the mass of Earth, and you can search the radius of Earth. And what you're going to see is the gravitational field strength turns out to be 9.81. Right. The other thing to note is we have taken a small value of altitude or a small value of h over here. Now, in the case that you are really far away from the surface of Earth, in that case, your h is going to actually affect the separation, the net separation, which is why the gravitational field strength, the gravity at that separation is going to change from your known value of gravitational field strength, that is 9.81. The other thing I want to mention over here is the amount of gravity or gravitational field strength is actually different at the North Pole and on the line of equator. Now, why does this happen? The reason is, compared to the North Pole, notice this image over here, our Earth is actually a bit bulged in terms of on the line of equator. What this means is the shape of Earth is actually a bit flattened. What this means is, if this was a perfect sphere, North Pole or the point of North Pole would have been over here. Now notice there is a difference in height, right? Now this causes the value of gravitational field strength to change over here. And why does that happen? Notice this point is closer to the center of Earth. So what that results in is your r square value, the separation squared, decreases. And what that results in is the ultimate gravitational field strength value to increase, which is why the gravity at the North Pole is higher than the gravity on the equator. So this is how the radius ends up affecting the value of gravity or gravitational field strength. Great. Now the other thing, I've partly already explained this, but the question is, why is G, gravity, constant near the surface of Earth? Now if you look at this diagram, if you compare this, consider this to be Earth, notice if you're really far away from Earth, the Earth would look like a normal round sphere, right? Which is why its gravitational field lines are supposed to be radial and be 90 degrees to the surface, meeting at the exact center. So it is supposed to have non-uniform or radial field lines. Notice the spacing between the field lines increase as you move away from the surface of Earth. Now what happens is, when you're really close to the surface, you cannot notice this curvature. You cannot notice that Earth is round. For example, if you go out on a walk, you're not going to notice the arc of Earth. You're not going to notice the curvature of Earth with your bare eyes, because Earth is massive, which is why the surface seems to be exactly straight, which is also why the field lines near the surface can be considered to be uniform, because it seems as though the surface is quite straight. And that is also why your field lines turns out to be approximately uniform, which is why up till a certain height above the surface, your amount of gravity or gravitational field strength does not change, because the field lines have uniform separation as you move away from the surface. Therefore, the field strength does not change much with small increase in height or altitude. Therefore, due to uniform field lines near the surface of Earth, your gravitational field strength stays approximately equal, which is 9.81, right? The next thing we're going to talk about is, how does gravitational field strength change as distance/radius varies? That is, if you have planet Earth over here, this is your center, this is your radius, and this is a distance away from the surface. How is the gravitational field strength going to vary? Now don't consider this part right now. Consider this part, which denotes the surface r, that is the radius. From the distance r from the center of mass to infinity, how is the gravitational field strength or the force going to vary? Let's see that. Now you know the formula for gravitational field strength, which is gravitational constant times mass of Earth divided by separation, right? Now notice one thing. As your distance increases, let's say from 1r to 2r, what's going to happen is gm, mass is going to stay the same, 2r whole square. So what has happened is, as the separation increased twice, your ultimate value of gravity is going to be decreased by a factor of 4. This is your gravitational field strength at the distance of 2r. At a distance of 2r, right? At this point. Therefore, as you increase your distance away from the surface of Earth, your gravitational field strength, or the amount of effect gravity will have, decreases. The amount of force exerted by Earth decreases. The attraction decreases, right? So moving away, the force will decrease. The field strength will decrease. The same curve can be drawn for the force because it will still have the same proportionality, that is 1 by r square, since in case of force there is another constant, that is mass of the object. Right? So in case of force, in case of field strength, the graph is going to be the same. I mean, not in terms of value, but in terms of the shape. The shape is going to be the same. Now, the other thing is, as I mentioned, as you move away from the center of Earth, your gravitational field strength will decrease with respect to 1 by r square. So if distance increases twice, your field strength will decrease 4 times. Great. Now, the interesting thing over here is how the gravity is going to vary inside the Earth. Now, what you have over here is the moment you go inside the Earth, there is mass on the surface pulling on you, and there is also mass inside the Earth pulling on you. Therefore, let's say you are at this position. You have some amount of mass on this outer rim, and you have some amount of mass inside the body. So there must be attraction from either side. Now, we can understand this better by deriving a formula to see how your gravitational field strength is going to vary as you go inside the Earth, right? So to do that, we're going to make a few assumptions. That is, first, let's consider the Earth to be uniform, meaning let's consider it to be a perfect sphere, and let's consider the distribution of mass to be uniform throughout the sphere, right? Let's consider the distribution to be uniform throughout the sphere. That means mass is equal at every point. And how is it going to affect? Let's see. So two things we need to have to derive this proportionality, that is the density. You know the density is mass by volume, that is of Earth. And the volume of Earth is 4 by 3 pi r cube. So from this, if you remove the constant, what you have is V is proportional to distance cube or separation cube. This is your first equation. Second part is the density. Density is mass by volume. So volume times rho, or density, is the mass. Since density is constant, we can say mass is proportional to volume. Remember, I asked you to consider the mass distribution to be the same. That is so that we can say this is a constant, because density throughout the volume is constant, right? Therefore, we can say mass is proportional to volume. So you have two equations. Now, if you equate both of these together, so V is common on either end. So we can say, cancel off the V, M is proportional to R cube. So you have this proportionality. And what we are going to do with this is, another formula that we derived in this video, that is gravitational field strength is Gm by R square. And you can omit the constant, that is G, and you can say G is proportional to M by R square, right? Great. So now you can bring in this proportionality over here and substitute in the place of M. What you're going to have is G is proportional to R cube divided by R square. And G is proportional to R. Therefore, considering the mass inside Earth, considering the volume of Earth, how does gravitational field strength vary? It is going to vary with respect to the radius, the linear radius, not squared, not cube, not to the power 3, just the radius. That means it's a linear increase / decrease in gravitational field strength with change in radius. Therefore, if you look at this curve, this straight line, how does gravity vary with distance inside the Earth? It goes from 0 at the center to the gravity on the surface. It turns out to be 9.81. So 9.81 on the surface, at the center 0, and it increases linearly. It's a straight line, right? And how did we prove this? Through this derivation. Great. Fair enough. So inside the Earth, the gravitational field strength varies proportionally with the separation, that is from the center. Okay, so in general, for the gravitational field strength graph, what you just need to know is the shape of the graph, how it varies inside Earth and outside Earth. You don't need to know the derivation. They won't ask you to derive this shape inside the Earth, but it's good to know in case it comes handy in the exam or in general. So the other thing I mentioned, remember I just said that at the center, the value of gravitational field strength is 0. Now, what you can understand from that is, let's say, where did it go? Let's say you dig a tunnel through the center of Earth. In that case, what you're going to notice is if you fall through the center of Earth, right at the center, your acceleration is 0. Why? Because your force right at the center of Earth is 0. Now, this example is better explained by this video, and I'll link this video in the description so you can watch the video, and it's quite well explained. So you'll get a better idea of what it means to fall through the center of Earth and how your velocity will vary with distance through the Earth, right? So I'll link the video, do watch it, it's a nice video. And that's going to be it for this video about gravitational field strength. We learned a number of things: A, the formula; B, the graph; and yeah, that's it. So see you in the next video.